All right. Hello, everyone. Thank you so much for joining us today at our live session. My name is Matthew, and I am one of the course developers and instructors for our online courses. And Alexander is helping us out with all of our behind-the-scenes technology stuff. And I'm going to hand this over to Professor Impey, who will get us started and ask for our first question.
Okay, welcome everyone for the Q&A session for the online classes, and the floor is open.
All right, the first question is from Junaid Atta, who's on with us live, who would like to know, does the sun always rise in the east and set in the west?
Yes, that's pretty much a fact of life. As long as the Earth continues to do, remembering that the sun rising and setting is actually a function of the Earth spinning on its axis. As long as the Earth keeps spinning in the same way that it is, that will always be the case. And pretty much the laws of physics say that's going to keep going for a very long time because the Earth has angular momentum due to its spin. And although that changes incredibly slowly over cosmic time, long term, it's not going to change at all.
All right, the next question is from Angelo Moro, who would like to know, if a singularity or a black hole is an infinite mass point in spacetime, why does its mass increase when regular matter falls beyond the event horizon?
That's a good question. The singularity is essentially a problem with the theory, so we shouldn't get too hung up on the singularity's implication, since it's like a fly in the ointment of black holes in the first place. The real definition of a black hole is the event horizon. That's the information barrier that divides the universe we can see from the universe we can't. And the mass of the black hole is essentially determined by the encompassed mass within that distance, the event horizon. The distribution of mass within the event horizon and the implication of a singularity is a part of the theory that's not fully developed.
All right, the next question is from Jerry Greer, who would like to know, are there stars that are solid carbon and with the pressures therein made of diamond?
Not exactly, but in a not too distant metaphorical way, yes. There are definitely carbon-rich stars, that is, stars a little more massive than the sun that have gone through the fusion cycle up to the creation of carbon, and then it stops because they're unable to collapse sufficiently to raise the temperature to fuse carbon into heavier elements. At that point, with no pressure support from fusion reactions, they collapse to a state of matter called degenerate matter, which is supported by quantum phenomena, basically the inability of, or the unwillingness of fundamental particles to occupy the same set of properties. That amounts to a kind of pressure. And that's the sort of white dwarf state. So some white dwarfs, the ones that have made a lot of carbon on their way to being white dwarfs, are indeed very largely carbon, some little bit of oxygen actually, and then helium and hydrogen left over from the fusion state. And they're at a density which approximates crystalline matter. It approximates solid matter. And it is a quasi-crystalline state. So even Pink Floyd had the ultimate rendition of this in their song Shine On You Crazy Diamond from the mid or early 1970s. I grew up on that music. Shine On You Crazy Diamond. And yes, in a certain sense, white dwarfs, the carbon-rich ones, are crazy diamonds in the sky.
The next question is from one of our live viewers. If a black hole is combined with a white hole, what would happen?
It's an interesting hypothetical. It's not anything that we can really test in the real universe, and it's not even anything we can easily work out theoretically. And that's because white holes are purely theoretical concepts or constructs. They're not as well developed as black holes, where the theory of black holes is quite mature. We have dozens or hundreds of examples, thousands and thousands if you count the big ones at the center of galaxies. And so we know their properties. A white hole is not, it's not obvious that gravity and our universe can create white holes, which is perhaps a portal from a black hole to another place in the universe where the energy can potentially escape. So the short answer is we don't know what would happen, because the one part of that pair, the white hole, is so hypothetical and so speculative that we don't even know how to calculate what would happen.
The next question is from CCC Laptop, who would like to know, is there a pink star?
Well, there are stars whose temperatures are low enough that they might appear to be dull red, but I don't think there's a star that's bright enough to be pink. So pink is a fairly warm color in terms of color, spectral color and painting color, for example. And also it has a certain intensity that we're used to pink being a sort of intensity. If you turn the intensity of pink down very far, then the way the eye receives it means that it'll probably start to look dull red. And definitely there are stars that look dull red. Betelgeuse is a giant in the sky in the constellation of Orion that clearly to the eye has a dull reddish tinge. So there are definitely red giants and red supergiants, which to most people's eyes appear dull reddish. But there's no star that has the spectral color and intensity that would make it look pink.
The next question is from Red Unleasher, who's on with us live, who would like to know, why is it that we have not found any medium or intermediate black holes just yet?
It's coming slowly. Basically, when I keep my eye on the research literature, every few weeks, certainly every month or so, there's a paper discovering intermediate mass black holes. It's a very hot research area to fill in the spectrum between the heaviest collapsed stars, the heaviest black holes, which may be 10 or 20 times, maybe 30 times the mass of the sun, and the lowest mass black holes that form at the centers of galaxies, which may be like 100,000 or maybe a few million. The galaxy's black hole is 4 million solar masses. So it's filling in the spectrum between just under 100 to just over 1 million. So there are black holes that are found in that range. There's some small dwarf galaxies that people look at where they've teased out black holes of maybe 100,000, 200,000 solar masses. Not many examples, but a few. And then there are globular clusters, that is dense old star cluster orbiting the Milky Way and other elliptical galaxies, where there are fairly good evidence of black holes that are 1,000, 10,000, 20,000 times the mass of the sun. Again, only a handful. It's very difficult to acquire evidence for them. But if you put all those individual examples together in a very sparse way, you're actually filling in the full spectrum of masses. So it's hard astronomical discovery work, but it is happening.
The next question is from Tony, who's on with us live. Is the map of the cosmic microwave background a map of how matter is distributed in the universe also?
Yes, indirectly. It's a radiation map of the universe when it was about 400,000 years old. So at a redshift of about 1,000, which means the universe was 1,000 times smaller, 1,000 times hotter, and 1 billion times denser than it is now. And what you're seeing with those microwaves is the radiation. Now, this was at a time when radiation was dominant. Radiation was dominant in the early phase of the universe, and then as it cooled, matter had a chance to dominate what went on and lead to the formation of structures. But the mass is subject to the radiation. And so in a sense, indirectly, the radiation map does map to the matter map and the fluctuations of mass in that early universe. And if you follow the evolution forward, then eventually the radiation diffuses and dims enough that it stops influencing the mass, and the mass grows according to only gravity without interactions with the radiation.
Next question is from Charlie Pierce, who's on with us live. What is the biggest challenge for astrobiology in the next 5 years?
I think it's pretty clear that with the instruments that are coming online, big new telescopes with star shades and the abilities with adaptive optics to image Earth-like planets, the big challenge in astrobiology, given that the technical side is sort of being covered by people who build instruments and telescopes, the challenge for astrobiology is developing enough knowledge of the range of properties of the atmospheres of habitable planets, depending on their microbial life forms, to make a prediction as to what their spectral features will look like if you made spectra of their atmospheres. In other words, astronomers are eventually going to produce spectra of reflected spectra of the atmospheres of Earth-like planets, maybe super-Earths and Earth-like planets, not around sun-like stars always, maybe around red dwarfs. And those spectra are not going to be very high quality because it's incredibly hard work and incredibly faint. And we're going to be seeing spectral features potentially due to oxygen, carbon dioxide, ozone, hydrogen, all the normal things that might be in an atmosphere. And the challenge for astrobiologists, when you have these real spectra that won't be as simple as you'd like, is to run enough models of what living planets and non-living planets can generate in terms of their atmospheric chemistry to be able to match these early data against models and have some confidence that you've been able to detect life. At the moment, it's not clear that it's going to be a sort of slam dunk experiment, to use the basketball analogy. So there's a lot of onus on astrobiologists to run very careful grids of models and prepare these models and the spectra and make them look like the spectra that are going to come from the telescopes, so that that comparison can be made in about 5 years, I think.
The next question is from an email. Megha Sharma asks, why is dark matter not supposed to be composed of many neutrinos? So what's the evidence that it's not neutrinos?
The main evidence that it's not neutrinos sort of preceded any measurement by physicists of what the mass of neutrinos might be. We still don't know the mass of neutrinos, but there are some pretty strong constraints now. But the real evidence that dark matter couldn't be neutrinos actually came from simulations and theory 20 or 30 years ago. Because if you put neutrinos into a cosmological simulation and evolve it, neutrinos have the property that at the time when matter and radiation decouple or part company, 500,000 years after the Big Bang, the neutrinos are traveling at close to the speed of light. They're relativistic. And that means, in the parlance of dark matter researchers, they're hot dark matter. And hot dark matter acts to erase small-scale structure. It just wipes it out because the neutrinos are moving so fast. And that means that the hierarchical structure formation from small to large does not proceed in the same way that it does if you have dark matter that's cold or subrelativistic. And very early on, again, 30 years ago, matches between the galaxy distribution in a hot dark matter universe and what we actually saw were just not very good at all. And the cold dark matter simulations matched what we saw. So people were pretty sure that neutrinos were not the dark matter quite a long time ago. The evidence since then has got stronger generally, but the door is still left a little open just because we don't know the actual mass of neutrinos. And they certainly have the cosmic abundance to be dark matter because there are as many neutrinos as there are any type of particle in the universe.
All right, thank you very much. The next question is from Jan Campos from an email. What is the possibility of another Copernican type discovery, one that upends our belief in how the universe works?
That's an interesting question. People always speculate about that. Are we in a time approaching a revolution in astronomy and physics, or are we just in a time of incremental progress towards greater understanding? Generally, we think the latter because things evolve fairly steadily, and as more data is acquired, it tends to affirm things that we already knew, like the Big Bang is the best model for the creation of the universe. Black holes we know exist and we're learning more about their properties, and so on. However, it's possible that there's a big paradigm shift on the order of the Copernican revolution in store, and most people think it's going to come in the arena of dark matter and dark energy, because after all, we still don't know the physical nature of those two things. And we don't have a good physics theory that even predicts them or explains them after the fact. And that indeed leaves open the possibility that there's a big change in our physics. And in fact, the physics is incomplete, so we know the physics is not the final theory. And that new theory could be as revolutionary as Einstein's theory was compared to Newton's, say, and that you would call a revolution.
Thank you. The next question is from Pamela Rodriguez Juarez, who would like to know, what can cause the death of a star?
All stars die naturally because all stars will eventually exhaust their fuel. So a star, by definition, is a large spherical cloud of plasma, so hot gas, which shines by its own energy release, and the energy release mechanism is fusion. So that's not an inexhaustible process. So it doesn't matter what mass or size the star is, eventually it will run out of nuclear fuel. So all stars will eventually die. And in general terms, the bigger a star is, the more massive it is, the hotter temperature it can create in its core, and the more rapidly its fusion reactions go. And so the quicker it runs out of fuel and dies. So ironically, the big stars in the universe, which have the most fuel, actually live the shortest lives because they burn through it at an enormous rate. Low mass stars like red dwarfs have the same process going, hydrogen fusing into helium, but they do it at a miserly rate, and so their fusion could last hundreds of billions years. The longest lived red dwarf could live close to 1 trillion years. But in the end, every star does die because every star will eventually run out of its nuclear fuel, however slowly it uses it. And so at that point, the energy mechanism is gone. There's no extra radiation coming out of the star, and it's essentially a cooling ember, a very hot gas ball, essentially just slowly cooling forever.
The next question is from one of our live viewers, Brian, who would like to know, can you explain black hole formation in the center of large galaxies? Does the black hole form first, or does the galaxy form first?
That chicken and egg question is really a very important research topic. It has been for a while, and it still is. And the reason it's unresolved is because galaxies formed and their central black holes pretty early in the universe, within the first billion years. And that's a time where and when the galaxies formed, the first ones that formed were actually quite small and therefore dim, and their black holes were quite small. So all of these things make it very hard to study them directly that far off in the universe and that far back in time. And so the answer is we don't know. At the moment, it's just been left to pure theory and some simulations to suggest which might be the case. And actually both work. It's possible to form a very first massive generation of stars. They tend to be more massive than the stars in the nearby universe. They can go up to 200 or 300 times the mass of the sun, which is sort of unprecedented mass for a star. And they will form pretty hefty black holes, 50, 60, maybe up to 100 times the mass of the sun. Black holes that big could be very good seeds for galaxies to form, and that means the galaxy would form around a black hole, and the two would grow together quite quickly. However, it is possible that the black holes don't form that abundantly that early, and so the small galaxies form first, and a slower process of mass getting to the center of those dwarf galaxies, whose gravity potential wells are quite shallow, so it does take a while. It's a slow process. That would mean the black holes grow rather more slowly. Now, if there's another argument on the table, it's that we see some quasars, some very luminous galaxies with very massive black holes, where a billion type solar mass black hole has been found within 500 million years of the Big Bang. And to grow a black hole that big, that quickly, almost certainly means it must have had a big seed, like 1,000 solar mass black hole seed. So observations of quasars are now starting to point to the fact that the black hole seeds probably formed first, and they may have been quite massive, like 1,000 times the mass of the sun.
Excellent. Thank you very much. The next question is from one of our live viewers who would like to know, why isn't the International Space Station absolutely covered in telescopes similar to the Hubble Space Telescope?
The International Space Station is actually a pretty crappy place to do astronomy, as it turns out. Astronomers were interested in the space station when they knew it would be launched. It is in a reasonably high orbit. It's higher than the Hubble Space Telescope orbit, for example. So there's not a problem with its orbit. The problem is it's just a bad environment for doing astronomy because it's a busy space station. It's always inhabited. There are people doing projects all the time. Some of those projects involve radiation being released, and some of them involve light or vibration. There are astronauts coming and going. There are spaceships coming and going to supply the space station and feed the astronauts. So it's just kind of a busy place, not as bad as like Grand Central Station in New York, but it's definitely busy, and it's not considered a bad radiation environment for doing astronomy. So astronomers have, even though it's convenient because we do visit it quite often, and shuttles are going there all the time, not shuttles anymore, but now it's going to be SpaceX going there. It's just not a very good environment for astronomy. It's much better to be further away from human activity.
All right, the next question is from one of our live viewers. Jugband Blues would like to know, are all nebulae that you see in the sky pretty much caused by a single dead star like a white dwarf?
The nebulae are an interesting category because it's sort of it's a morphological designation. It's a description of something in the sky that looks fuzzy or nebulous. And you know, the classic catalog of nebulae is, of course, the Messier catalog. Messier was a comet hunter in the late 18th century. So in 1789 or so, he released this set of 100 or so objects, which were essentially non-comets. Comets move on the sky, and the Messier catalog was a warning list for astronomers to avoid, since there weren't comets, which is what he was interested in. Of course, it's become the go-to list for amateur astronomy. And they really only united by being fuzzy objects in the sky. And if you look at what they are, they're all sorts of things. A number are galaxies, about 25% I think are galaxies. About another quarter are star-forming regions. Another roughly quarter or maybe less are supernova remnants. Some are planetary nebulae. And so if you look at what this set of nebulous objects are, they're in about 5, 6, or 7 different categories. So calling something a nebula is a very simple descriptive term, but it unfortunately doesn't tell you what it is at all.
All right, the next question is from Doctress Nutopia. I'm getting into stargazing of the night sky. Are the laser pointers useful or dangerous in pointing out stars? Is there a particular one to use? Can they interfere with air traffic?
Yes, good question. I mean, I know a number of amateur astronomers, and laser pointers are definitely are reasonable and good equipment to have as an amateur astronomer, especially if you're going to give star parties or guiding people around the night sky. Most amateur astronomers know what they're doing, and they don't need to have the sky pointed out to them or pointed out to themselves. But the few amateur astronomers I know in Tucson that I've been out with at night, they all have laser pointers. They tend to use a longish wavelength red laser because, of course, that helps not to spoil your dark adaptation. Most amateur astronomers use red LEDs or red lights on all their equipment, or anytime they need a light, and the laser pointer would be the same thing. And these lasers are fairly low power, so these are pretty standard lasers. They work well enough. There's enough aerosols and particulates in the air that even a low-powered red laser pointer, the kind you can buy for $20 or $30, will do perfectly well to illuminate a sight line in the sky, and it's not a danger to aviation. I think the lasers that do that are dangerous like that, apart from how they're pointed, are about 5 or 10 watts or larger. You can get away with a couple of watts or less for an amateur astronomy laser.
All right, the next question is from Jerry Greer. Is there a theoretical limit to star size? And if so, what is that size?
There is, but it's a very vague, or it's an imprecise limit, annoyingly imprecise. We have really powerful supercomputers now, and we can simulate what happens when a large gas cloud collapses. And there is a natural physical limit to the size of a star, because although there's nothing to stop a gas cloud of 200, 300, 500, 1,000 times the mass of the sun from collapsing spherically by gravity, what happens beyond a certain mass is that the collapse, the free fall gravitational collapse, is so violent that the object disrupts before it has a time to form a coherent object, even if there's rotation in the picture. And the point at which that happens is a little unclear, but it's around 150 times the mass of the sun. So in most simulations and computer models of stars, that's roughly the upper bound to star mass. And for the most part, astronomers observing stars and measuring their masses when they can in binary systems agree with that limit. Every now and then there's a claim in the literature of a star that's 200, 220, 250 times the mass of the sun. And I don't think most of those have stood the test of time. It's very hard to measure star mass accurately in astronomy. So the theoretical limit seems to hold.
Next question is from Melvin Cohen. I saw on PBS that there are so many dams in the northern hemisphere that they have caused the Earth's tilt to alter slightly. Is that the case? And if so, how does it work?
So many dams. That's an interesting. I haven't seen that article. I know that there are claims, that earthquakes or other seismic activity, if it were not symmetrically distributed around the Earth, might cause the Earth's tilt to change. I've never heard of dams causing that, and it's actually hard to imagine how that could be the case. The largest, the most profound potential to change the shape of the Earth, which is really what you need to change its tilt, would come from seismic activity or earthquake activity, when plates are moving and rearranging and subducting and so on. And even that, I think, in the modeling of it, is not really enough to change the Earth's tilt by an amount that's measurable. Now, I suppose in principle, there are extremely tiny changes to the tilt caused by, geologic motions in the Earth and seismic activity, but nobody's ever measured anything like that.
The next question is from Alistair Brown, who says, hello from the UK. With the advent of adaptive optics, what are the main advantages of space telescopes for light and, so I'm assuming optical and near infrared, for example, James-Webb imaging versus ground-based or high altitude?
Right. Hello back to the UK from someone who's from the UK. The advantages of space, there are still advantages from space. The sharpest image ever taken of an astronomical object, actually, I can say proudly, was taken at the Magellan Telescope by one of my colleagues, Laird Close, and his group with adaptive optics just 2 years ago. Published, it got on the New York Times front page because it was sharper than the Hubble image of the same object, scaled by telescope size and so on. But there are niches, or significant niches, for which space is still better. Infrared is one of them, because on the ground you're in a different thermal environment. You're dealing with a planet at a temperature of 270, 260 Kelvin, and that creates infrared radiation. So all infrared observations from the ground are fighting against the background of the terrestrial environment. And as soon as you go into space, you can radiatively cool a telescope like the James-Webb or the Hubble down to 10 or 20 degrees Kelvin. So for infrared observations, space will always be better than the ground. It's also still better in some ways for optical observing because of the background. So when you measure faint stars and galaxies on the sky, they're not set against an absolutely black background. It's not like detecting light against absolute black. The sky has a brightness. And measured from the Earth, the sky brightness is very dark if you go to a beautiful site like Hawaii or Chile, but it's not absolutely dark because the atmosphere has a dim glow, and that's independent of the moon. So just assume the moon's nowhere in the picture. That comes purely from air glow, residual air glow from energy deposited into the atmosphere by cities and industry and then spread around there's sort of transient air glow effects that come from cosmic rays that come into the atmosphere and energize particles. So the air actually glows very dimly. And you have to fight against that glow. When you're in orbit, you don't have that glow. You're in a vacuum. There's no atmosphere. So for this reason, space is always going to be darker than a terrestrial environment for visible observing.
All right, the next question is from Yana, who sent an email and would like to know generally about turbulent and turbulence phenomena in space. So first of all, how does turbulence manifest in space? And are things like the spiral structure of the Milky Way similar to turbulent forces like whirlpools?
Turbulence is a very important phenomenon in astrophysics. It's well known and well studied in physics. It's classical physics from 200 years ago. Its examples in the universe are many. There are turbulent gas flows that come out of hot stars. There are turbulent ionized gas flows that come out of black holes. There's turbulence in the early universe when there was a certain amount of sort of chaotic disorder superimposed on the general cosmic expansion. And I could make a long list. So turbulence really is found in many astrophysical contexts because everything is not completely orderly. There's always a random component. That random component, often has a thermal reason because you're talking about the chaotic motions of things that have fundamentally random motions at a microscopic level. So turbulence is important, and people found that they actually couldn't make good theories of how stars form until they took into account the turbulent motions in the gas cloud out of which stars form. They found they couldn't make good models of how galaxies formed in the same way. So turbulence is present in all these different scales. It's one of these interestingly scale-free phenomena where it manifests on all scales, from a forming solar system to a forming star to a forming galaxy to the universe itself. So it is extremely important in astrophysics.
All right, the next question is from one of our live viewers. Ashaz Punjani would like to know, why does a comet look like a shooting star?
Well, comets have several components when they're close to the sun. Of course, comets far from the sun, which is where most of them are for most of their time, are in the Oort cloud, tens of thousands of astronomical units away, receiving almost no solar radiation, and they're just essentially inert rocks mixed with ice. But they're, just irregular shaped rocks. They have no gas around them. When comets start to look like shooting stars, it's when they're close to the sun, when the sun's energy and radiation evaporate the volatile materials, the frozen gases and liquids, and send that off plus ionized particles into a stream behind the comet. And it has a coma, that's a region of hot gas, ionized gas right around it, and then it has a tail which streams away from the sun, the direction away from the sun, driven by the sun's radiation. It's a different thing from a shooting star because a shooting star is a very transient phenomena. Comets have tails and have that appearance as long as they're close to the sun in their orbits, and that will reoccur the next time they're that close to the sun. A shooting star is the death throes of a small particle in the upper atmosphere. People are usually surprised when they realize that a typical shooting star is actually a particle probably no bigger than a grain of sand and probably 100,000 or higher feet up in the atmosphere, but coming in at an incredible speed of tens of thousands of miles per hour. And that kinetic energy turning into heat energy is what creates the appearance of a shooting star, but it lasts a very short time. So most shooting stars are extremely transient. They last barely a second or a few seconds. Only the biggest pieces of space junk coming in and burning up in the atmosphere last more than a couple of seconds.
Thank you. The next question is from Pashupati, who sent an email asking, what is the fate of stars like Betelgeuse and Antares?
They will have very violent demises. They will get unstable late in their life. As a star gets to the later phases of nuclear fusion and ascends up the periodic table towards iron, which is the most stable element, the time for the fusion cycle gets shorter and shorter, and the previous fusion cycles continue to take place in shells around the star, so it has an onion skin structure. It's very unstable because it's a large object, and anytime there's a change in the fusion rate, the star has to react to that. When eventually it reaches the most stable element, iron, then it stops generating enough energy to resist collapse, and so it collapses, and then you have a violent explosion called a supernova. So that's the fate of those two massive stars that you mentioned and all other massive stars. And it's a very rapid final phase of evolution of a star that may have been millions of years on the main sequence, it may spend only weeks or days in the last few fusion phases before the core collapse and the detonation as a supernova.
So a few questions about stars. So the next question, and then maybe you can answer a more general case. So would we be in danger specifically if the star Vega went supernova? And then more generally, what is the closest star that could affect us, could, cause damaging effects to us on Earth?
I don't remember the exact distance to Vega, but it's not close enough or massive enough to die as a supernova, big enough and dangerous enough for the Earth to have a problem. I know that. So it's not in the watch list of the most massive stars closest to the Earth. So we don't need to worry about that. Was the second part of the question, what is the most dangerous star?
Yeah, are there any stars that are close enough to us to cause danger, or how close would a star have to be dangerous?
Yeah, so the people who do the surveys for potential threats to the Earth caused by, the violent death of a star nearby, we pretty much know the census of stars within 100, 200 light years. We don't know the census of all the dwarf stars in that volume because they can be very dim. But the massive stars, the ones that can die violently, we certainly know where they are. And they're mostly known, their evolutionary stages. And I think last time I saw an article about this, there are only a handful, and probably only even one, that are close enough, which is to say probably less than 20 light years away, and massive enough and close enough to the end of their life that they could plausibly die within, say, not our lifetime, but a civilization's lifetime. We can't measure their evolutionary state accurately enough to say they're within 10 years or 100 years of dying. We could only possibly say they're within a millennium of dying. And so there's a small handful of stars that are in this situation. They're all bright enough to easily observe. Small telescopes, amateur astronomers can observe some of them with their networks of 10 or 20-inch telescopes. So they're under close watch. And if any of them gets unstable and really looks like it's heading to its death throes, so we'll know about it. You'll read about it in the newspaper.
The next question is from Sean Knight, who is on with us live. Since the Earth is becoming a dangerous place for humans, will humans be able to move to another planet or moon in the coming decades or centuries?
It's a very difficult prospect. As you probably know, in the years before he died, Stephen Hawking sounded the alarm. He basically had looked at all the existential threats to humanity, and we all know what they are. They're climate change, they're nuclear weapons, bioweapons, destruction of the biome by other means than climate change. And he just thought, we better have a plan B. We better have a backup plan for where to go and what to do if we mess up the Earth so badly we can't live here. Unfortunately, the simple answer is no. There's no prospect for a plan B, not on the timescale of a few decades. The minimum timescale for a plan B is centuries, really, because there's no habitable place close to us. The Mars is obviously the nearest place. People have talked about terraforming and rendering habitable, but the cost and time and energy required to make Mars habitable is formidable. And again, it's not anything that could happen in decades, even if we started right now. And we don't have the wherewithal or the technology or the money to do it right now. The exoplanets, the Earth-like exoplanets, the nearest bet, I suppose, for one is Proxima Centauri, 4.5 light years away. Again, no way any significant number of people could ever get there, or now nobody could get there. We have no interstellar travel, and even in the foreseeable future, not clear how that would work. So while Hawking's admonition has to be taken seriously, help is not on the horizon. And so in a sense, it's a good thing. The answer becomes simple. We pretty much have to take care of our planet.
The next question is from Pam Lamb, who would like to know if space has an odor.
Interesting question. Not in general, because space is essentially nothing. So space is an almost perfect vacuum. The average density of the universe, or the intergalactic space in particular, is about 1 atom, which means 1 proton or fundamental particle, in 10 or 20 cubic meters of space. like the size of a room. That's incredibly small density. The average air you're breathing would have 100 billion times more atoms in that volume. So incredibly low density, and obviously that doesn't have a smell. However, there are odors in space. There are molecules that even scientists who don't tend to use evocative language call aromatic molecules. And some of these do include molecules that would have smells. And the places where most of these smelly molecules, if you like, are in star-forming regions, because star-forming regions, before the stars form and start heating everything up and getting hot, are actually cold, dense places where molecules form. There are some molecular clouds with 100 different species of molecules, and they include acetylene, ethyl alcohol. They include some of the basic simple chemicals. These typically are molecules with no more than 20 or 25 atoms, but they include variants of some of the chemicals that give bananas their smell, that give some acid type smells or acerbic smells. Hydrogen sulfide, of course, that's a very simple molecule. That's just sulfur gas. And that exists in these star-forming regions. So actually, probably 7 or 8 molecules that we would say in significant quantities are smelly that exist in star-forming regions. However, in those regions, they're still at the density so low that with our olfactory equipment, we would never be able to smell them.
All right, the next question is from Aryan Chubi, who sent an email. What will happen or would happen if another star equal to the size of the sun were to come into our solar system?
It would be very bad news, even if it were nothing close to an impact or a grazing encounter with the Earth. Let's just say it came into our solar system and never got closer, say, than the sun is to the Earth. So it's not a question of this rogue star making the Earth uninhabitable. Or maybe it's just a passing encounter. Maybe it just passes by about, say, twice the distance from the sun. Well, that sounds like it would be fun, exciting. The Earth would heat up for a while and then cool back down again. The problem is that a star coming into the inner solar system or anywhere deep into the solar system would actually wreak havoc with the orbits of the planets. And very likely, if it had some passing encounter in the inner solar system, would disrupt one or more inner planet orbits enough to eject those planets from the system. So even if we survived the close passage of a sun-like star, because it didn't get too close to us, it's quite likely that the aftermath of that would be the ejection of the Earth from its orbit, most likely to a situation where there was not enough solar energy to sustain life on Earth. So we pretty much hope this won't happen.
The next question is from Alejandra, who is asking a historical question. So if you know anything about the conversation between Galileo and Kepler, apparently Galileo said no to Kepler's request for a telescope. Do you know why that was?
Yes, it's not a, I've read some of the, obviously translated some of the pieces of the correspondence. It's a little bit of a bad story about Galileo, actually. I mean, Galileo was a tricky customer. He we know he got in trouble with the church, and he was on the right side of history on that one. But he also had a little bit of a willful streak. At the time he was getting in trouble with the church, it was pretty clear what was going to happen, and he had many offers to come and work in the UK and British universities where there was no problem with the Catholic Church, and Germany and Holland, I think. And he just didn't want to go there, and he was sort of saying, bring it on. So he had a stubborn streak. With Kepler, it was a little a frustrating story too, because Kepler did indeed ask for one of Galileo's telescopes after he'd improved it by pretty much a factor of 10 in its visual acuity from the first model that he made. And Galileo, remember, correspondence was difficult back in those days. I mean, sending a letter somewhere elsewhere in Europe could take months, basically, or weeks at the best. So correspondence was this kind of sketchy thing. But there were exchanges of correspondence, and Galileo just essentially ignored. I mean, he didn't overtly say, I'm not going to ever send you a telescope, don't even ask me. But he sort of blew him off and never really addressed it. And at the time, he was dealing with his own issues, so maybe he was distracted, who knows. But, looking at it from a distance, it really doesn't seem it would have been that hard for Galileo to give Kepler a telescope. And Kepler deserved it. He was a preeminent mathematician and astronomer. He also was extremely myopic, so it's not even clear that Kepler would have been able to use this telescope, given his own visual acuity problems. And then it even got another layer, because when Galileo was under the Inquisition and had had his first warning from the church to stop teaching the heliocentric system, unbidden, Kepler wrote a letter on Galileo's behalf to Cardinal Bellarmine, the Pope's inquisitor, if you like, who was prosecuting Galileo for his beliefs. And it was a very strong and heartfelt supporting letter. So after being spurned by Galileo, Kepler was still a good enough man to write a letter of support. So it kind of leaves a bad taste in your mouth thinking about Galileo for that episode.
All right, the next question is from Jim McLeod, who is on with us live. Taking advantage of more modern equipment, does someone do Eddington-like observations of stars near the sun with every total solar eclipse to look for relativistic effects?
It can be done. So the Eddington experiment you're referring to was the one that happened in 1919. The general relativity theory was published in 1916 during the First World War. And just after the war, Eddington led an eclipse expedition to measure the deflection of the starlight grazing the sun's limb, where general relativity predicts a different deflection angle from Newtonian gravity. And it was viewed as a strong and spectacular affirmation of relativity soon after the fact. We can do, not every solar eclipse is suitable. Remember, it's not just an eclipse. You also need an eclipse where a relatively bright star happens to be near the limb of the sun at the time of the eclipse. And so you can measure the deflection. So not every eclipse is suitable. But there have been a number of eclipses since 100 years where we could do the experiment. And to my knowledge, it's been done several times more. It's no longer considered a cutting edge or state-of-the-art test of general relativity, because you can't do that experiment, that measurement, accurately enough to improve on any of the other tests we already have of general relativity. So at the moment, it's not a sort of state-of-the-art experiment. It's still an interesting thing to do if you have the opportunity.
All right, the next question is from Hernan Reyes. Apparently there was an intense debate between two schools about how thick the icy crust of Europa is or might be. Some people think it might be 100 or maybe several hundred kilometers thick, and some European astronomers think it might be much thinner and permeable. What are your thoughts on the thickness of the crust of ice on Europa?
Right. I'm aware of this. There have been actually couple of scientific meetings in the last 4 or 5 years just on this particular issue in those community of planetary scientists. It's because it's so controversial, it's fairly easy to decide. I'm not an expert in this particular field. I just sort of keep loose tabs on it and ask my colleagues in planetary science across the street. It's pretty easy to decide that we just don't have enough information to decide the proposition. And it's pretty clear why. We haven't been to Europa for decades. The Europa Clipper mission has been funded and approved, and so we are on this within sight of a new mission to go to Europa, but it's over a decade before that mission gets built and launched and gets to the moon of Jupiter. We just need more data. We need another generation of instruments, which would be 30 or 40 years better than the instruments that went there in the 1970s, would be able to answer all these questions definitively. You don't even need a lander to do it. Just using magnetometers, using high-resolution imaging, spectroscopy, seismic measurements, gravimetric measurements when you vary the orbit in an elliptical orbit. So it can be completely decided, not only whether it's thick or thin generally, but whether there are thick and thin parts. One of the issues when you want to send a lander is, what if you could melt down through the ice with a nuclear power plant and actually explore the subsurface, the ocean, or the bathysphere or a hydrosphere? And so you'd want to find the thinnest place. And there's the thin crust school argue that there are places where liquid is seeping through cracks towards the surface and then, of course, evaporating and freezing into space. And again, you just need new data to decide between these two things. So basically, this is one of those arguments that they'll keep having until we get more data.
All right, the next question is from one of our live participants, Red and Leisure, would like to know, how can a neutron star that is neutral also be a magnet?
Oh, that's a good question. So the electric and magnetic phenomena of stars do not have to be closely related, intrinsically related. It is true, as in Faraday and electromagnetic theory, that if you have a changing electric field, you can generate a magnetic field, and vice versa. So those phenomena are coupled, but the causation of them, the origination of them, is not the same. So in a neutron star, because the process of forming the star has caused a reverse version of beta decay to occur, you have lost your electrons and protons and replaced them with neutrons. So the neutron star is indeed electrically neutral. It may have about 10 to the 57 neutrons in it, but it's essentially a neutral object. However, the star had a magnetic field when it was a regular star, and as the star collapsed and shrank to its small state after nuclear fusion was over, the plasma of the star traps the magnetic field, just like the sun traps its own magnetic field. And so as the star collapsed, it squeezed the magnetic field. And so you end up with a star that is electrically neutral, because it always was, and that didn't change when you made neutrons out of the electrons and protons. And it also has an incredibly strong magnetic field, because the original magnetic field has been amplified phenomenally by the contraction or compression of the star. And so that's the state you end up with, a very bizarre state of a neutron star, which can have strong magnetic properties, and the blemishes on a neutron star obviously give rise to pulsars.
All right, thank you very much. The next question is from Stardust Sagittarius, who is on with us live. Do you think it's possible to travel near, at, or faster than the speed of light? And other people would like to know your thoughts on things like the warp drive or Alcubierre drive.
Yeah, I'll answer them separately. So for relativistic travel, for physical objects like humans or spacecraft, the energy requirements are just formidable. It's actually almost a freshman level physics exercise to figure out how much energy would be required to put a human mass, a 70 kilogram or 100 kilos, moving at 90% of the speed of light. And I don't remember the actual number, but it's very large. It's like the energy requirement of a big city for a year or something. So just a phenomenal amount of energy to make any macroscopic object go anything close to the speed of light. So it's not something that's really feasible in the near future, because we just don't have the means to harness enough energy to make that happen. On the other question of whether it's possible to have a warp drive or Alcubierre drive, which is a physicist in just at the edge of the mainstream, I would say, who had this provocative idea for warp drive and faster than light travel, which seemed to be rooted in the laws of physics. That's been very controversial work. I don't keep in touch with that literature directly, except to know that both the idea hasn't gone away. It's had a fair amount of pushback from conventional physicists who don't really think it works or don't think the physics is completely valid. So as we speak, no, there's no part of the current structure of physics that can accommodate faster than light travel. The concept of a tachyon, or a faster than light particle, a sort of mirror image of a particle, a normal particle which asymptotically reaches the speed of light. A tachyon starts at the speed of light and accelerates upward from that. A tachyon is a theoretical construct that had never had any experimental evidence. So even at the level of subatomic particles, there's no sign of faster than light travel. It will be complicated too, because you create some philosophical issues. If you had a mixture of lower than light and faster than light speed travel, you could create situations where causality was violated. And that's a foundational problem for physics and philosophy, actually. So for various reasons, I don't think faster than light travel is possible.
Excellent. Thank you very much. The next question is from one of our live participants. Vifon would like to know, when will we be able to deflect asteroids away from Earth if it became necessary? And what technology might be the most successful at accomplishing this?
We could do it now. We have the technology to deflect an asteroid given sufficient notice. And that by that I would mean probably a couple of years notice to get the wherewithal and build the mission to do it. It sounds like a long time, like surely we don't have that much time, but the answer is we do have that much time, because the people with small telescope arrays monitoring incoming objects and Earth crossing asteroids have done a pretty good job at finding almost everything larger than 200 meters anywhere in the inner solar system. So anything we picked up with our telescopes that was moving in our way will be a few years from getting to us. So if we had that time, what's the best strategy? It's not to blow it up. Don't send in the nukes and explode it, because conservation of momentum means that you just end up with a lot of shrapnel continuing in the same direction, and the shrapnel of a big asteroid is big enough to take out a small country each piece, so you don't want to do that. And you can't send beams of radiation or ion beams or any other sort of futuristic sounding beamed energy to deflect or ablate the asteroid. You can't ablate it either. You can't burn it up or burn it off. The best strategy is actually kind of a pedestrian strategy, but it's one that we actually know we can do because we've landed on comets with spacecraft. So basically you just send spacecraft with a detachable probe, a massive probe in this case, so it's quite a hefty spacecraft, out to the incoming object, and then turn around to track it in its incoming trajectory. And you release a subsidiary rocket, or maybe it's the main rocket that lands on the asteroid, and then drills down and essentially tethers itself into the asteroid. So it's built to do this. It has to know what the thing is made of so that it can drill deep enough and tether itself firmly enough. And then it uses its retros pointing upward to deflect, essentially make a transverse impulse, which will cause a slight deflection to the trajectory of the object. And the longer you do the burn, the more the deflection, and the further away the object is when you do it, the less you have to deflect it for it to, the long lever arm to mean that it's enough to miss the Earth. And so that strategy, all the pieces of it actually are in place. We could do that. If we really had to, we could set that mission up today.
Excellent, thank you. The next question is from one of our live viewers, Jugband Blues. Is a black hole a good place to look for strings? And I'm assuming that means that it's referring to information or evidence of string theory.
Right. We don't know. I don't want to say no because we simply don't know. At the moment, it's proving very hard to find observational evidence of strings. Black holes are extreme situations, and the only place where since we cannot see inside the event horizon, the only place where we might potentially get evidence that strings exist is at or near the event horizon, the place where, for example, Hawking radiation occurs, and so virtual particle-antiparticle pairs are disrupted at the event horizon, leading to the net emission of radiation or matter. I have not seen any prediction that would say that you could detect strings in that situation or that location, and I haven't really seen many predictions of how you detect them with high-energy accelerators because they simply don't go to high enough energies. The best arguments I've seen in experimental physics are for sort of almost tabletop scale experiments, so experiments on scales of meters or millimeters, which look for very tiny deviations in the structure of space-time on these mesoscales of the laboratory as a hint that strings might exist, or that there's granularity in space-time at a very fine level. And even then, they are not really feasible experiments as far as I can tell. So I don't think black holes help us in this regard, but I'm sure there's some clever people thinking of more ideas.
The next question is from Ranjan Mutia, who asks, since the Earth likely formed from a cloud of differentiated material, iron to light atmospheric elements. Have we looked for or have similar clouds been found elsewhere?
Yes, in the places where we think stars are currently forming, Orion Nebula is a region 1,400 light years away where stars are forming right now. We can look at the process by which stars and planets form, and in the few cases where it's happening close enough, we can see that a gas cloud that's collapsing to form a star and its subsequent planets is chemically differentiating as it collapses. Now we can only see that at the level of the star. At the level of the planets, there's no system close enough that we can see differentiation of a protoplanet as it forms. That's just beyond a scale available to us. So at the moment, we're still relying pretty much on simulations and theory to say what we think happens.
All right, the next question, and I believe this will be the final question for today. So Malik Saad asks, is string theory a theory of everything? If not, then why does Michio Kaku have so much confidence in this theory for explaining the origins of the universe?
Well, I know Michio fairly well. I was on his radio show just a couple of weeks ago. I think he has confidence in it because it's really the only thing we have. It's the only viable theory of everything, where there's been a lot of theoretical work, where there's certainly some promise in the theory, where it's accounted for with great effort in the work of the theorists, some conventional physics, but it hasn't made any unique new predictions that can be tested. So unfortunately, it's come down to that. It's just very hard to find theories that are self-consistent, that are calculable, and then even harder, that are testable, which unify quantum theory and general relativity. And string theory is one of those. And it's been around for 30 years now. And some progress has been made, and some like Brian Greene and Michio Kaku are quite optimistic, and there are others like Steven Weinberg, other very famous physicists, who are not so optimistic and don't think that it's panning out. And time will tell, I guess, but it's been around for long enough that some people are starting to get frustrated by that lack of progress and are starting to cast around for other ideas. But nothing else has come up that's as exciting as string theory yet, so you'll have to stay tuned for that. Thanks for all your questions. Great range of topics as usual, asteroids to string theory. And we'll be back with you in a little over a week, I guess. And the next 2 dates will be announced together for the next few weeks. Thank you, and thanks to Matthew and Alexander for helping the session.